journals and conferences too. Thank you very much, ma'am, for your presence. Now I'm inviting Dr. Asvija sir and handovering the session to sir. Thank you very much for giving this opportunity.
So I am Asvija, and topic for quantum constellation with begin with I start with Astakam thereof Namaya Vishad. Either I'm an expert in or I'm an expert in Vedanta. First, I can just position myself as a student in. Nevertheless, today's talk I'll just look at consciousness related aspects of quantum mechanics. I will try to highlight similarities Vedantic and how they consciousness. For the discussion, I will try to focus and here in the purposefully omitted the reference. Obvious. I have just included the references typically here. In other cases where the things are very obvious, I have omitted the references in the slides as. Before I begin, I have heavily borrowed the content for my presentation today from the lectures and videos from all these eminent scholars. Most of the content that I'll be presenting today will be a summary of talks and the presentation delivered by all of these different scholars as well. I'll start by introducing some weird quantum mechanical concepts which will give us a fundamental understanding of why study of consciousness or the relevance of consciousness is in terms of understanding quantum mechanics or quantum physics. Now, this is the famous experiment called as the double slit experiment, which we start any discussion of mechanics as. Whenever we speak of quantum physics or quantum mechanics as, we generally deal with very small particles, subatomic particles, or atoms by themselves. So we are dealing in that scale. Of course, the laws of quantum physics apply to macroscopic objects also, but the effects are not that pronounced. Effects of quantum behavior will be very much pronounced in the kind of small particles. So this is an experiment which will have a slit. You know what is a slit? Opening cardboard. We will have two openings. That's why this experiment double slit. And there is a source in keep emitting single particles. In this case, we take this emitting electrons as. Okay? So these electrons are thought to be as particles. This source will be continuously emitting these single electrons, and it will be made to pass through these two slits. It means it is just an opening. There are two openings. So what do we generally expect? If we have a screen on the other side which captures how many electrons have been passing through. So this is the fundamental idea. Just have a source of electrons. Keep firing, just like how the bullets get fired from a gun. Keep firing the electron. I have a double slit which locks or which allows the, and then on the other side of it I have the screen which captures how many pass through the. Now, if the electrons are particles as such, then the expected behavior is that you will get two vertical strips on the screen. Means to say that the electrons have passed through the two slits or the two openings. Right? So that is the general expected. There should be only two bars which represent the electrons passing through two slits. Right? But on the contrary, if this setup is allowed to run for a while, okay, and then if you observe the pattern on the screen, you see those kinds of multiple bars that appear on the screen. Okay, so instead of just having two bars which represent the two slits that are there in the obstruction that we have kept, right? So instead of having only two bars, we will expect that it will have multiple bars like that. Okay, so that's called an interference pattern. People from the physics background, you might be knowing what an interference pattern is, right? Now, how can this be explained? If electrons are particles, then how do we expect to have this kind of multiple bars, which can come only if the electrons are behaving as waves, right? So you can see the example in the bottom figure, wherein there are waves, okay, and if the waves are allowed to pass through the same kind of double slit, okay, so you have again two openings over here. Now in this case, instead of having particles, we are allowing the waves to pass through this, right? Now the waves will pass through these slits, and you know how a wave is represented. It will have a crest and a trough, right? So the crests, if both the crests are matching in phase, then we have something called as a constructive interference, because of which the amplitude will get increased. If the troughs are matching, then the crest and the trough is matching, then we will have something called as a destructive interference, because of which the amplitude will get reduced, right? Now, this is what gives rise to the interference kind of pattern that is visible on the bottommost side. So, if the electrons are to display the kind of pattern that is being displayed in the top figure, then they obviously have to behave as waves, which means to say that they are not behaving like particles, right? The same thing will happen when we try to conduct the experiment using photons, okay? So if we start emitting photons are again particles of light, right? So if we start emitting photons as such, then you are again observe the same kind of behavior. So you get an interference pattern which clearly indicates that these particles are behaving as waves rather than as particles, okay? Now this might be very simple. If we just adopt the wave behavior for the photons or the electrons, then we can give the explanation why the interference pattern is coming, right? Now what is so weird is that, let us say that if I have some kind of apparatus which will try to monitor how many electrons or how many photons have passed through any particular slit as such, okay? So if I just attach an apparatus here, a counter here, just to indicate how many electrons have passed through this slit, either slit A or slit B, okay? So if I have any apparatus which measures how many electrons have passed through, then surprisingly, the interference pattern will completely vanish, okay? It will be exactly behaving as if the electrons are particles, as if the photons are particles. That means to say that you will only get two bars which represent that the particles are behaving in a particle-like manner. So the wave nature of this entire particles will just vanish and they will behave exactly like particle. So you remove the counter, you allow the system to work on its own, then again the interference pattern emerges, okay? The moment you try to see what is happening, I mean how many particles are going through any of these slits, then again the wave nature will collapse and you will be able to see only the particle nature. So this is something very strange in the quantum physics as such, okay? So the transition from wave-like behavior to particle-like behavior, what exactly causes this? Okay, so when you try to observe a system, then the wave nature of these particles will be collapsed, and you will be able to see only the particle behavior of these particles, right? So this is something weird. So this is what is called as the observer effect. So when somebody is looking at it, the particle will be localized in space-time, okay? It will display the particle behavior. If somebody is not looking at it, if somebody is not observing the system, then it will display the wave behavior, okay? So this is something very weird or very counterintuitive to what we generally expect from the physical systems as such. So, yeah. Huh. Yes. Let us say that we are talking about some electromagnetic waves. Electromagnetic waves, let us say. If we send a wave, we know that the waves interfere, and we are expecting that it will generate an interference pattern, okay? But in case of the quantum particles as such, the wave behavior will completely vanish when somebody is trying to look at how exactly the particles are going through in the system, okay? Now, this phenomenon is called as quantum superposition. This is again somewhat related to what we have already understood with the double slit experiment. At C-DAC, what we have been trying to do is to make use of these kind of properties that are available in the quantum particles, be it the quantum superposition or quantum entanglement and things like that. How we can make use of these kind of behavior to build useful computers or communication systems, okay? So that is what C-DAC has been into, to harness these kind of physical properties that are available with the quantum particles as such. How do we build a quantum computer or a quantum communication system by making use of these kind of quantum mechanics specific properties of the particles as such? Now, one of the important properties that these particles display is called as the quantum superposition. Basically, let us say that we choose a particular quantum particle, be it an electron or a photon or whatever it is. They have some intrinsic properties, right? And these properties can have different values, okay? Now, when I try to do the measurement, they can have different values associated. Let us take one example of an electron. Now, the electron has a property called as the spin, okay? Now, the spin is usually assigned a direction, okay, depending upon the right-hand rule as such. Just for the sake of simplicity, we will assume that there are two types of spins. One is called the up spin, the other one is called as the down spin, okay? So, when I try to see a particular electron, I will be getting either the electron will be in the up spin or in the down spin, right? Now, what is interesting is these electrons, as it is, they will be in a state of superposition, which means to say that they will be in both of these states, up and down, at the same time, okay? Whereas, when I try to see exactly, or when I try to measure what is the spin of a particular electron, then it will suddenly collapse, and I'll be able to get either an up spin or a down spin, okay? But if I'm not observing the system, then the system will be in a superposition state, which means to say that it is in the state of both up and down at the same time. So the same thing is depicted in the diagram on the right side. If I call the down spin as 0, if I call the up spin as 1, then what I mean to say is that if I'm not observing the system, then that system will be in a state of both 0 and 1 at the same time. Okay, so this is what is called as quantum superposition, and this particular representation of encoding the values of zeros and ones into the quantum particles, this is what we make use of in building quantum computers as such. So the quantum computers make use of this quantum superposition principle for encoding the informations in terms of zeros and ones. Okay. So why are quantum computers interesting? Because when we use a qubit, the right-hand side representation, as you can see, it already encodes the information about both 0 and 1 simultaneously. Whereas in a classical system, in the traditional way we do computing, you can have the bit value either as 0 or 1 at any given point of time, right? Whereas in a quantum computing system, you can encode the information with both 0 and 1 at the same time into a qubit. Now, this is what gives rise to what is called as quantum parallelism as such, and that is why the quantum computers are considered to be much powerful when compared to the classical computing systems as such. Yes, it will be ambiguous. It carries the information of both 0 and 1 at the same time. But the interesting thing is, when you try to measure that particular quantum state, it will collapse either to 0 or 1. It gives a definitive answer of 0 or 1 when you try to measure it. Okay, so that is what it says. Superposition is a fundamental concept in quantum mechanics, describing the condition in which a quantum system can exist in multiple states or configurations simultaneously. Now, the example that I have taken in this particular slide has only 2 levels of 0 and 1. It need not be limited only to 0 and 1. It can be multi-level system. And in fact, people have been trying to build quantum computing systems also by making use of these multi-level systems as such. They're called as qubits and qubits and things like that. Anyhow, we will just limit to only these 2 different states as such. Okay. Now, the important thing is the state of superposition can be maintained only while a quantum system is unobserved. Okay, so the moment there is an observation made on this quantum state, it will collapse either to 0 or 1. Mathematically, to represent such a system, we use something called as a quantum wave function. Okay, psi, the Greek letter psi is the standard letter that is used for representing this quantum wave function. So here, as you can see, this is the way mathematically it is represented as a linear combination of both 0 and 1, okay, with some amplitudes over here, alpha and beta. Now, the entire information about that particular quantum state is said to be embedded in something called as a quantum wave function. Okay? So this is what represents the quantum wave function, and the numbers over here, the alpha and beta, they represent the amplitudes, the complex amplitudes of this wave function. What is the significance of this alpha and beta? Now, alpha square and beta square, when we do the square of these numbers, they give the probability with which this state will collapse to 0 and this state will collapse to 1 when I try to do the measurement. So when I try to do the measurement of this particular particle, I said that when I try to do the measurement, it will collapse to 0 or 1, either 0 or 1. Right? What is the probability with which I get 0 is determined by this factor over here called as alpha. What is the probability with which it will collapse to the state of 1 is determined by this number over here called beta. So alpha square gives the probability of measuring 0 and beta square gives the probability of measuring the value as 1. Okay, so I already talked about the quantum wave function. So it's a mathematical description of the quantum state of an isolated quantum system as such. So inherently, the quantum state is a specification for every experiment that can be performed on the system of probabilities for the possible outcomes of that experiment. So there are probabilities associated whenever you try to do the measurement on a particular quantum state as such. Now with this, the underlying statement is that the application of quantum theory typically involves a distinction between the system under study, that is the quantum state itself, which is treated quantum mechanically, and an experimental apparatus which is not. So you cannot apply the same quantum theory to the system that you are trying to study and the person who is trying to study or the experimental apparatus itself. So there is a clear distinction between the state that we are trying to study and the observer or the person who is trying to study the system. Okay. So this division is sometimes called as the Heisenberg cut or the Heisenberg cut, again named after the famous physicist Heisenberg, who has given us the Heisenberg's uncertainty principle as such. Now this is the famous equation called the Schrodinger's equation, which governs how the quantum state evolves in time. Okay, so given a quantum state of any particular quantum particle as such, how does it evolve over time? Okay, so what is the kind of change that it goes through in time? So this equation has been a fundamental discovery in terms of quantum mechanics, which was given by Erwin Schrödinger, which earned him the Nobel Prize. So basically, it talks about how the energy of the quantum state evolves over time as such, using the operator called the Hamiltonian. We'll not go into the description of that. It is just sufficient to understand that this equation governs how the quantum state will evolve over time if the system is an isolated system allowed to evolve as such. So if it is allowed to evolve as such on its own, it will be evolving governed by this particular equation. What happens when you try to measure or when you try to observe this particular system? So we earlier saw that if a particular quantum particle is allowed to exist as it is, it will be in the state of superposition. Whereas when you try to measure or when you try to observe that particular quantum state, then this happens, something called as a collapse happens. So we saw that the quantum information, the quantum state, was represented using the mathematical formulation of a quantum wave function as such. Okay. Now when you try to observe, this wave function is said to collapse. Okay, which means to say that the quantum wave function ceases to exist and it becomes completely classical. Okay, so when you try to observe, it becomes classical. Classical means what we generally experience in our world with all the macroscopic objects over here, the binary notion. Whereas if you just try to allow the system to exist as it is without having any observation or measurement done on it, then it will continue to evolve governing this equation of Schrodinger's as such. So there is a clear distinction that the Schrodinger's equation cannot be applied once you try to measure or observe that particular quantum state. Okay. So that's what it says. Unlike the unitary evolution applied otherwise, the unitary evolution is the Schrodinger's equation, the evolution that is governed by Schrodinger's equation, which I just mentioned in the previous slide. This is a discontinuous change. What is the discontinuous change? The collapse is the discontinuous change of the quantum state, which is sometimes referred to as the collapse of the state vector or the state vector reduction. So what is the implication of this? There are two kinds of interpretations about this. So if the quantum state represents nothing more than the knowledge about the system, then once we collapse it, it is just upgrading the knowledge that we already have about the system. It will collapse to either of the classical states, 0 and 1. So it is just an updation of the knowledge of what we already have with the system. However, if the quantum states represent physical reality as such, because we are talking about electrons and photons and the subatomic particles, which we know are the fundamental constituents of matter as such, right? So if the quantum states represent physical reality in such a way that the distinct pure states always represent distinct physical states of affairs, then the collapse postulate entails an abrupt, perhaps discontinuous change of the physical state of the system. Okay, so these systems will be in some particular state and they will be evolving unitarily, which is governed by the Schrodinger's equation. But when you try to do an observation, then it collapses this entire system and it gives an abrupt and a discontinuous change of the physical state from the quantum state to the classical state. So this problem of not having the same physical theory that can explain the quantum system as such and the classical system as such, there is a discontinuity between both of these explanations. Okay, when it comes to the quantum state as such, we apply the Schrodinger's equation and we know that the system evolves in that manner. Whereas when you try to make an observation or when you try to make a measurement there, that theory or that particular equation will no longer hold good. Okay, so it completely collapses to the classical scenario as such, and the laws of quantum physics as such do not apply over there. So there is a discontinuity with this kind of observation or with this kind of measurement as such. So this problem is called as the measurement problem in quantum mechanics. So standard quantum mechanics works very well as long as you are not observing the system, as long as you are not interfering with the system as such. It works very well with the states getting evolved as per the Schrodinger's equation itself. However, if you want to have one theory which is capable of describing all the systems, including the macroscopic ones, which can yield the account of the process for all the macroscopic events that we are encountering in day-to-day life, then this is where the measurement problem comes in. So there is no unifying theory as such which tells about the state of these kind of systems before and after doing the measurement. Okay. So this particular problem has been studied in detail by many of the physicists, both philosophers as well as quantum physicists as such, and to this day there is no consensus and there is no unifying theory on how to address this measurement problem as such. In fact, Bell, J.S. Bell, who is again regarded as one of the forefathers of quantum information sciences as such, we have the famous Bell's inequality theorem, and many particular interesting quantum states which have been named as Bell states in honor of Bell, who has contributed significantly for the advancement of quantum information science as such. He has remarked that either the wave function as given by the Schrodinger's equation is not everything, or it is not right. Okay. Okay, so how does this compare to our Vedantic view of the systems as such? Now this is again a verse from the Brihadaranyaka Upanishad, which says, Dvevava Brahmano Rupe Murtam Chaiva Amurtancha. Okay, now as I've been telling till now, there are two distinct states. One is the quantum state, the other one is the classical state. Okay, and in between, this boundary is where the consciousness or the measurement kicks in. Okay, so the early proponents of quantum mechanics, including Schrodinger himself, felt that unless there is a conscious observer, the system will be evolving as such, governing with the quantum mechanics as such. Whereas when there is a conscious observer introduced into the system, then the system will collapse to what is called as the classical state as such. So this boundary is governed by consciousness as such. Okay.
Is there any definition that consciousness actually?
There is no consciousness definition coming from quantum mechanics as such, but it assumes that there is a conscious observer who will introduce this kind of collapse from the quantum state to the classical state. And this is where the definition of consciousness and other things will come in from the Indian knowledge systems, which I'll just try to explain in future slides. Yeah, so if we compare with the kind of explanation that we have, it also talks of having two different states as such, right? Murtam and then Amurtam. So this is the Murta Rupa and this is the Amurta, right? Martyam cha Amrutam. This is the Martya, right? This, all the classical things that we see around us is all here. And then the Amrutam, these are the pure quantum states as such. Okay, this, and quantum states as such are again pure energy states, right? Then again, Sitancha. Okay, yeah. Sthitancha, this is the sthita state. Yatcha, we are talking about having the wave function over here, right? Satcha, so this is the sat state, and then tyatcha. So we have already started seeing the analogy between the Vedantic system of thought and what quantum mechanics is also trying to propose. Moving on, we have another famous thought experiment in quantum mechanics called as the Wigner's friend experiment. So this whole experiment is again a thought experiment devised by Nobel Award winning physicist called as Paul Wigner, a Hungarian physicist. He was awarded the Nobel Prize for his phenomenal work on the particle physics as such. Right? Now, what he proposes is, if I have a quantum state in a lab, let us say that there is some particular quantum state which is kept under observation, and if there is another entity, in this case a friend of Wigner, okay, so that is what is represented as F over here, and if Wigner asks his friend to observe this system, okay, now we are introducing a two-level observation into the system. So all this while we were talking about directly observing the quantum systems as such, right? Now we are introducing a two-level observation into the system. So if Wigner asks his friend to observe what is happening with the quantum state inside the lab, okay? Now the quantum state will be in this state of superposition, right? Whereas when she observes the system, it will collapse to either of one state, right? Either 0 or 1, and that will be communicated in turn to Wigner. Okay? So she is the direct observer of the system, and once she observes that it has collapsed either to 0 or 1, this information has to be conveyed back to Wigner. Now, what happens when this information has not been conveyed to Wigner? Okay? Assume that the friend has already seen or observed the system. At this state, the system would have collapsed to 0 or 1, right? But Wigner doesn't know what is the state of the system yet, right? Because he has not inquired with his friend what is the kind of result that she has got with the experiment. So in this state, for him, the entire system is still in a state of superposition. The system was originally in 0, and the friend has also measured it as 0. The system was in the state of 1, and she has measured it as 1. Okay? So only when he makes a query to his friend, then he will know whether the result was 0 or 1. Right? What it means is that we are trying to introduce one more level of superposition, which involves a conscious being over here. Right? So earlier we talked about having superposition with the quantum particles as such. Okay? Now we are extending the idea of superposition to include the human beings or the conscious beings also. Of course, when did the actual collapse occur? When did the actual collapse of this system occur? Just because Wigner has not asked his friend, does it mean that the quantum collapse did not happen? It might have happened when the friend has already observed the system. Okay? So when exactly did the collapse occur? So these kind of questions get arised from this thought experiment called as the Wigner's friend experiment. So was it when the friend had finished their measurement, or when the information of its result entered into Wigner's consciousness as such? Okay. Now obviously you cannot have the superposition of having the person into the system also as such, and the system should have got collapsed when she makes the observation on the system as such. But then if that is the case, then how do we all see the same kind of classical objects if somebody is trying to collapse the quantum state as such by their own observation? Okay? If I have my own friend, and if they are trying to collapse the system, then how am I able to see the same system which has got reduced or which has got collapsed because of someone else's consciousness? Okay. So the obvious answer is that the earlier proponents of quantum mechanics came to a conclusion that because of these kind of weirdness, because of these kind of unanswerable questions, the consciousness at least should be shared among all the beings in the universe. So the idea of having a shared consciousness is what was proposed by the early proponents of the quantum mechanics, including Schrödinger himself. Now, you can see the direct correlation between the thinking of the Vedantic systems, which also propagate the same idea of having a shared consciousness among all the sentient beings in the world.
So what is the experiment output of that?
Now, this is a thought experiment which will lead to the questions like this. So these kind of questions, again, if you have to come up with an explanation for this, people have come up with different theories, but Wigner himself was in agreement that there should be a shared consciousness between all the people as such, if the outcomes have to be in sync between all the people as such.
Indian philosophy says that consciousness is universal.
Consciousness is universal, yes.
Probably shared indicates that
It is shared and it is universal as well, yeah.
when you were presenting, I thought that the outcome should be universal.
Yes, yeah.
Immediately when Werner asked immediately that amounts to observation.
Correct, correct, yeah. Irrespective of whether Wigner asks or not, his friend, whenever she tries to make the observation itself, the system would have got collapsed. Okay, anyhow, I have been instructed that only 5 minutes are available. I had some more slides, so I'll just rush through.
So will you please give more focus on how our Vedanta?
Yes, yeah, I'll just come to that part quickly. So these are the extracts that I have taken from the lectures of Schrödinger himself, who is considered to be the foremost, the father of quantum mechanics as such, who has given the Schrödinger equation. So he says that the reason why our sentient, percipient and thinking ego is met nowhere within our scientific world picture can be easily be indicated in 7 words, because it is itself that world picture. Okay. It is identical with the whole and therefore cannot be contained in it as a part of it. You can directly see the correlation between the Vedantic's view and his views as such. Okay. The several domains of private consciousness partly overlap. The region common to all, where they all overlap, is the construct real world around us. So if this kind of consciousness, if this kind of unified consciousness is what we are talking about, is my world really the same as yours? Is there one real world to be distinguished from its pictures introjected by way of perception into every one of us? You can see that these are all the fundamental questions that our Upanishads have been asking, right? And if so, are these pictures like unto the real world, or is the latter, the world in itself, perhaps very different from the one that we perceive? So there is obviously one alternative, namely the unification of minds or the consciousnesses. Their multiplicity is only apparent. In truth, there is only one mind. Okay. The world extended in space and time is only but our representation, right? This again very much fitting to the Vedantic views, and he has rightly recognized that this is the doctrine of the Upanishads. Okay, since there is lack of time, I'll just rush through these things as such. Then there are these reductionist theories which talk about the consciousness itself can be completely explained using any of the physical processes as such, which can be reduced to either the physical or the chemical processes as such. This will be involving the neurological studies of the brain as such, and how brain can give rise to consciousness and things like that. But then there is a fundamental difference between these theories, the reductionist theories, and what the Vedantic system adopts, in what is called as the hard problem of consciousness. People who have been doing some philosophical studies, you might be already be aware of what is called as the hard problem of consciousness. This refers to the subjective experience of the individual as such. Okay. There is an explanatory gap between a third person encounter of what conscious experiences are and how I personally feel as a first person experience. In fact, there have been different papers which have been published, like what is it like to be a bat, just taking an example of a bat as such, and how a first person experience for a bat could be completely different from how we see what is the kind of perception that the bat is having. Okay. Now, this is exactly what our Vedantic systems have been propounding, of laying the highest importance on the self-inquiry process or on the subjective experience as such. So, what is consciousness? The definition of consciousness, again ma'am was asking. We know our systems define it very well, and they have put it very precisely. Anidam Chaitanyam. So, anything that you point out as this cannot be consciousness. So, it has to be completely subjective experience, right? So, that is where it says neti, neti. Okay. So, anything that you point out as an objective process as such cannot be the consciousness itself. So, it has to be completely subjective, and which cannot be explained as such, which cannot be replicated as such, right. Of course, there have been many efforts in the kind of reductionist studies as such, in trying to see how the quantum effects could be produced in the human brain. Today Sudarshan sir was also mentioning about how the human brain can perform the computations of a large language model, the LLM or the ChatGPT equivalent kind of things. We humans, we are very much capable of understanding the natural language in a very easy manner, right? I mean, we don't have to impart any programming logic into our system just to understand any natural language as such. So, to understand how the human brain functions, neurologists have been trying to locate the various functionalities of the brains as such, and they have been trying to map the functionalities of the brain, the different organs, the different components of the brain as such into specific perceptions as such. Quantum consciousness again is one of the branches of these studies, which stresses on the quantum reduction or whatever the quantum collapse that we just discussed. These theories say that the quantum collapse happens in the human brain. Okay. Because there is a conscious observer that is required to collapse the state from the quantum to the classical. How are we able to see the classical world around us? These physicists, including Sir Roger Penrose, who is again a Nobel laureate, a famous mathematician and a physicist, he has proposed this theory called as the objective reduction, the OR, which highlights that the quantum collapse happens in the human brain. But then he also says that the consciousness itself is incomputable. Okay, this is again very much in sync with the Vedantic thinking as such, wherein we have all these sample statements which I have taken. Na vidmo, na vijanimo, right? I mean, if you want to replicate the consciousness, it is impossible. That is what he has been telling. And he takes the shelter of what is called as Gödel's theorem in mathematics, mathematical logic as such, which puts a fundamental limit of what can be proved using mathematical statements, right? And he also says that consciousness cannot be computed or consciousness cannot be replicated as such on the computational systems, which puts a fundamental limit on what the AI systems can achieve even in the future. Okay. So, the subjective experience as such cannot be replicated, and this is something completely uncomputable. When I say uncomputable, people from computer science domain, you might be knowing what we mean by computability of something, right? We are talking about the Turing hypothesis. Okay. Consciousness is something incomputable which cannot be modeled as a Turing process as such, right? And because of this, it cannot be replicated also in the systems as such. So, all the AI systems that we plan to develop also lack the subjective experience of the consciousness as such. Yeah, so these are some of the details of the OR theory itself on how the microtubules in the neurons, the brain neurons, will cause the quantum state reduction as such. I'll not go into the details because of the lack of time as such. Then there is another principle called as the quantum pleasure principle. Again, I have not added any specific reference for this, which gives the analogy with our Vedantic thought, because the whole idea itself, you can draw the analogy by yourself. Now, what it says is that can pleasure act as a feedback function for reducing these states, right? They go back to the state of how the life itself got formed with what is called as the Miller's experiment, when they try to mimic the creation of the molecules in the lab, okay, the fundamental, the primitive biomolecules which got synthesized, which again gave birth to different forms of life as such. Those simple molecules, the primitive biomolecules, if they could synthesize in the lab, right? Now, all of these molecules, they had this kind of structure in common, called as the pi resonance groups, right? Now, what is the particular preferred state for this particular structure? Okay, if one particular combination or if one particular configuration is preferable, we see that there is only one particular configuration that is repeated in most of these biomolecules as such, whereas the other kind of unpreferred molecules is not taken care at all. So, what is the fundamental principle that has given rise to this kind of preference in the configuration? Can pleasure be seen as a feedback function? Now, this again goes back to the Vedantic view of having Ananda as the prime goal, or the entire system built around Ananda. Can that be the primary driving force for having what we see as the origins of life itself? Okay, so summary and conclusion, I have already talked about all these aspects. Both quantum consciousness and Vedanta, they explore consciousness as fundamental to reality. Consciousness is not emergent, but it is foundational. Both of these theories, they challenge the classical materialism and reductionist models. Reality arises from a non-classical formless substratum, and they emphasize on the observer's central role in shaping the experience, and the subject to object distinction is ultimately illusory. We of course need a new paradigm which will open the pathways for this kind of interdisciplinary understanding of integrating quantum mechanics and the Vedanta's philosophical framework, which can reveal new perspectives on consciousness, which could also be a holistic approach which combines the modern scientific and the Vedantic views. The Vedantic views can offer more comprehensive understanding of consciousness as such, because the Vedanta lays the emphasis on the self-inquiry, and we have sophisticated models available with Vedanta on the self-inquiry as such. Today again Ganapati Bhatt sir mentioned about buddhi, the entire buddhi itself as an adhyasa, right? So, we have the adhyaropa apavada or the avasthatraya or the panchakosha. All of these excellent tools are already available with the Vedanta for the self-inquiry as such. So, can these models be incorporated in doing the consciousness studies to give a holistic approach of this entire field itself? Again, to conclude, what is the ultimate benefit? Why do we need to even do the study on the consciousness? Of course, in the modern science, the study of consciousness is just like any other field of study. Okay, it is a branch of the neurological sciences as such, right? So, like any other medical science or any other neurological science, we are just interested in knowing how the things work, or why does this happen at the fundamental level as such, right? Whereas in the Vedantic system as such, the fruits of the Brahma Vidya or the Atma Vidya was something much greater. The ultimate aim or the ultimate fruit of all of these things was bhaya, shoka, moha, nivrittaye. So, it has a very deep benefit to the individual or the self as such. So, if you know the self or if you know the Atman, then it will lead or it will alleviate the bhaya, moha and shoka as such, which is exactly is desired by all the human beings. So the consciousness studies from the Vedantic perspective gives a much holistic approach, contributing to the spiritual growth and the inner growth of the individual as such. And of course, the ultimate fruit, bhidyate hruday grantihi chidyante sarva samshaya. So this has been the ultimate goal of all our Brahma Vidya studies as such, which leads to what is called as moksha. With the moksha could be either attained when you are alive as such, with the person getting awakened as such. So if we can have this kind of interdisciplinary study incorporating the Vedantic studies into the modern scientific consciousness related studies, then definitely that will be a holistic approach, and that is where we will all have to work together. Okay, with this I conclude this talk. Applications, I said this is the broad application, this is the ultimate application as such. But then, like I said, this can also aid the study of the modern consciousness studies as well. For example, any of the neurological studies that people have been taking, including the OR model that I just mentioned, they do not take into the account of the avastha trayas that our Vedantas explain it so beautifully. So if these kind of studies can give better insights to the neurological studies as such, then that will be great. Yeah. This one? Huh. No, they are separable, because that is what I told. I told that this measurement is a discontinuous process. The collapse is a discontinuous process. The moment you do a collapse, this will get reduced to this. So there is no nonlinear separation at all over here. It is an abrupt change from here to here. Okay. So any other questions?
Sir, I have a question.
Yes, sir.
So there are some beliefs like we worship statues.
Yeah.
So we worship statues, and then we worship different objects which are not necessarily human.
Yeah.
So which are not living, actually, non-living objects.
Okay.
With great respect, we do worship them. So it is also believed that they have consciousness. Like people convey their worries or express their joy to Vigraha. Let us say Lord Narayana Vigraha is there.
Correct.
You feel that he is conscious.
Yeah.
So consciousness, is it only limited to neurons and living entities, or can it be for?
Not necessarily, sir. I mean, in fact, if you see this picture itself, I told you that this boundary is what consciousness is depicting. Now, if we talk about our Vedantic systems, the different schools of Vedanta itself, for example, in case of Advaita, we consider this entire thing as one whole, including the consciousness itself, right? The quantum states, the things that we see around us, and the consciousness, everything becomes one big sphere. Whereas we have the Visishtadvaita, where we have the Chit, Achit, Ishvara, the kind of distinction. And if this consciousness can be clubbed in any of these spheres as such, for example, if this can be moved to this state, then we have this same thing giving rise to the Dvaita philosophy. So we have the two distinct systems. And in fact, people have been talking about how the consciousness can get entangled. There is another concept called as quantum entanglement, which I did not talk about because of lack of time. So the human consciousness can get entangled with any of the systems as such, the physical systems as such. So that is again a separate field of study. But yes, people have been looking at all of these aspects, and there have been many theories in this respect also. Sir. Thank you, sir. Thank you. Yeah.
Might be different, right?
Yeah.
Based on your quantum
together also,
Yeah.
what I see might be different compared to the person sitting next to me.
Yeah.
Is that right, based on quantum state?
No, that is what. So that is what this experiment was all about.
Okay.
If this friend sees this particular state, and if she has got some result, how is it that he also will be able to see the same result? Okay, unless there is a shared consciousness within all the human beings, this may not be possible. And that is where the conclusion of having a shared single consciousness which pervades all the human beings is what is thought of.
See, here basically it is like this person is seeing that and she's conveying it to him. What if two people are seeing the same?
Yes, the same thing will happen. For example, let us say that she has already seen, okay, and he will also enter the same room without asking her. He will also be able to see what she has collapsed already, right?
Okay.
Uh,
So it won't be some other state which he will see if he has come a little late
yes,
or something
yes,
like that?
Yeah, because it is a shared consciousness, the moment it gets collapsed over here, it will also get collapsed to him. So that is that is one of the ways in which the theories are explained on telling how the views from two different persons will also yield the same kind of result.
Thank you.
Yeah. Yes, ma'am.
Subjective and objective differences are
Is this the one?
illusionary. Not this one. Maybe last slide or before the last slide.
This one?
No, little bit further. I think in the summary, sir. The last one, subject and objective distinction
Yes.
is ultimately illusion. I didn't get that. What is the subject and object distinction here?
Subjective experience is what is called as the first person experience. How you perceive the things. For example, the usual example says like, how do you feel when you taste something which is sweet, okay, or when you see a particular color as such. How does it feel to you? This is exactly what I was trying to explain with this, what is called as the hard problem of consciousness. The subjective experience is what is called as the hard problem of consciousness, whereas there are other problems which can be explained, which are also not that hard, which are called as the easy problems of consciousness. The objective experiences is what is called as the easy problem. The subjective experience is very hard to explain or to replicate as such. So that is what is called as the subjective experience. Like I said, for example, how does it feel like tasting a sweet? Okay, if I place the sugar on my tongue, only you know what it feels like tasting the sweet as such. So that is completely subjective as such. Okay, there might be theories on how the subjective experience occurs. For example, the molecules will be broken, and then your tongue has some kind of receptors. They will react to the kind of molecules that are there. All of these are all objective processes as such. The subjective process is the experience that you try to feel by yourself. The sweetness as such is completely subjective. So that cannot be explained by anyone else who is watching this process. So for him, it will be an objective process. But only you as an experience, it will be a completely subjective process for you. Yeah. Yes, that is where it was said that the subjective experience of the consciousness itself cannot be replicated and it cannot be computed as such. So if you try to compute, let us say that you are asking the computer to mimic the functionality of consciousness. Nevertheless, it cannot mimic the subjective experience itself as such. So in that sense, it becomes incomputable as such. Thank you. If there are no more questions, thank you.
It is a very good privilege and honor to listen to the lecture and really enjoyed a lot. I am not a subject expert, but still it gives a lot of explanation about our spiritual questions also. And he talked about double slit experiment. So when the normally when an atom gets divided into smallest particles, their behavior can be studied in quantum physics. If I'm wrong, you can correct it, sir. But that behavior, very recently, even in the last workshop conducted by the computer science department, one professor asked us this question. People are saying that in our Vedanta we have everything. Does our Vedanta explains this? The question posed was that when observed, the smallest particle behaves differently. How it happens? When it is observed, it starts moving. When it is not observed, it stays still. So how does that happen? That means how does electron knows that it is being observed? And do you any classical spiritual text of Indian tradition has the answer for that? Probably Asvija, am I pronouncing your name rightly? He answered his question, and really I enjoyed it a lot. And also, if there are any questions, I know that there are many people who are interested in this. You can have a discussion with him at lunch, or you can take his number and can, if you want, if you can both work together as a research scholar for the questions posed by the quantum physics also. Thank you very much. And if you say, and I have a doubt, and just I'm saying it. Whenever we say consciousness, does it includes ego or not? That's the question. But consciousness, as far as I understand, it doesn't have ego. When there is ego, there will not be the behavioral change. These are the questions to be answered right now. And I request our Ganapati Bhatt garu to felicitate Asvija garu. Thank you. You can select the book. There are 2 books. Afterwards, you can select the books. And now we have, all are requested to have lunch at backside of Sujala, and I request you, all of you, to finish